We've just seen an example of computing an inverse function to the z² function. That was our z to the 1/2 example. In example 6, we're going to just briefly remind ourselves about inverse functions and how to go about finding them. There is nothing here that you haven't seen before. We're just working in the realm of complex numbers. So let me remind you that for an inverse function to exist, so for inverse function, usually it's written f inverse, f upper -1 to exist, we need that f is 1-to-1 and onto. So this function is the translate function. Translation is always 1-to-1 and onto. It's 1-to-1 because if 2 points have the same translet, they must come from the same location. So if you add 3i to two complex numbers and you get the same thing, the original complex numbers had to have been the same. So f of z1 equals f of z2 would tell us that, oops, didn't highlight that, would tell us that z1 plus 3i equals z2 plus 3i, would tell us that z1 is z2. Okay, so if two inputs have the same output, they must have been the same input. Great. And then it needs to be onto. So with onto, given any w in C, we need z in the domain C such that f of z is w. So how do you find such a w? How do you find such a z that outputs the w? Well, our function is just translate by 3i, so we should translate by -3i to find the thing that translates to us. Said differently, we can just solve this. So z plus 3i is w. So that tells us z is w minus 3i. And that's it. So if I have a w, how do I find the z? Well, I translate the w downwards 3. Now this also tells us what the inverse function is. I'm going to write it as a function of w. Your book doesn't do that. It writes it as a function of z. But I want to indicate that this comes from the w plane. And that's it. That's the inverse function. And the way in which we check in which an inverse function exists is it needs to be 1-to-1 on the domain and onto on the domain. Now let me take a minute here and point something out. Z², so note well, Z² is not 1-to-1, but it is onto. And so there's sort of two ways to go about fixing this. The easiest way, since it's already onto, every number is the square of something. Why? Because we have a formula for taking two square roots. The way in which we fix this is usually we fix the 1-to-1 problem by restricting the domain so that it becomes 1-to-1. Now this is something that you already understand from the normal square root function. Namely, we don't consider all real numbers as the codomain of the square root function. We think about just the positive real numbers, or the non-negative ones rather. Same thing, we're going to do the same thing here. Now I'm going to try to draw the domain. For various reasons, we'll want to adjust our domain, but usually what we'll regard as the domain, so the z, I'm just going to say z domain, is usually we're going to regard it to be a set that is solid here and then open on the negative imaginary axis, and then we're going to consider all points here. Okay. Now, if we consider this as our input domain, then all of a sudden z² is 1-to-1, because those problems, the problem with the squaring function not being one-to-one is usually you'll have a z1 and then the negative version of that going to the same spot. Now, unless of course you're 0, in which case you're equal to your negatives. But for almost all complex numbers, z1 and negative z1 have the same square. And so what we do is we cut this in half. And what that does is it gets rid of this other input. So now our function is one-to-one. And now we can define an inverse function. So the inverse to the squaring function is, of course, the square root function. And that square root function actually outputs stuff here because we use the principal argument. And that's why we use the principal argument, so that we're in the right range. So okay, so this was sort of a tangent on the idea of an inverse function. But the point is that most functions are not invertible, but we have this process of fixing it, of adjusting the domain so that it becomes invertible.